Good morning, kids. We'll discuss today the total internal reflection. The topic name will be total internal reflection. This will be our topic name, total internal reflection. Okay, now what is the total internal? We'll see like this. If a ray of light, let this be the incident ray. So here, let this be the angle of incidence. This is the boundary, so let this be the rarer medium. Mu r. Let this be the denser medium. Mu d. And this will be the normal. And this will be, we'll call this as a boundary. Boundary or an interface. So the ray of light, now it is moving from denser medium to rarer medium. Definitely the ray will undergo refraction. It will bend away from normal. There's a typical path. Agreed? So now after refraction, the ray will bend like this. And this will be the angle of refraction. This is the angle of incidence. So what is the angle of incidence? This is the angle of incidence. Angle of refraction, this angle of refraction. As the ray is moving from denser to rarer, it will bend away from normal. You can check it. It's bending away from normal. Okay, now, what is the Snell's law? The Snell's law says that sine mu d sine I equal to mu r sine r. As I increases, proportional when r must increase. As I increases, as this angle increases, definitely the r has to increase. From the sense now. Now I'll increase the angle of incidence. Then for one specific angle, the refracted ray, which is here, no, as the angle of refraction increases, for one specific angle of incidence, the refracted ray will graze the boundary. This condition will represent here the refracted ray. This is the refracted ray we have chosen. Some other color, let me choose here. The refracted ray will graze the boundary. You can check it here. So the angle at which the refracted ray grazes boundary, that will call that as critical angle. So then we'll apply the Snell's law. Here refracted ray grazes boundary. Then mu d sine c equal to mu r sine 90 degree, or sine of critical angle is equal to mu r by mu d. Then if I further increase the angle of incidence, the ray will get totally internally reflected. No further the ray, what will happen? The ray will get internally reflected. All the energy will be reflected back. This condition is what we'll call as a TIR, or in short, we'll call this as TI, total internal reflection. All the energy will be reflected back. The total energy of the system will be reflected back. Then what is the condition for TI? The angle of incidence, this particular thing, this angle of incidence If it is greater than or equal to critical angle, the ray will undergo total internal reflection. So here after we'll write here for TIR, the angle of must be greater than or equal to critical angle. Okay, like this, there's a basic idea of the. So when do we see the TIR? Only when the ray moves from, this denser medium to rarer medium. We'll see this TIR. Agreed? Huh? No. If the rarer medium is air, we'll analyze next condition. If the rarer medium is air, if this is a rarer medium, if this rarer medium is air, the denser medium, let it be glass. Then we can define the critical angle. The critical angle for glass we can define like this. So this is the critical angle. So what is the value of critical angle? This will become equal to mu g sine c is equal to refractiveness of air is mu air into sine 90. Mu g sine c. We'll write here critical angle for glass. This should be equal to 1 into 1. Like this, we can define critical angle for a pair of a medium. The critical angle will be defined for a pair of medium. What is the pair of medium here now? Glass and air. Similarly, we can define the critical angle for some different medium. So that what is the different medium? Let me choose glass and water. So what is the critical angle? Critical angle here will be call C, then mu G, and let this be mu W. This is the incident ray. This is a refracted ray. Now, how the ray is moving from the glass will graze the boundary and it will finally be moving like this. This angle will be 90 degree. Then, okay, they will indicate this angle. This will be 90 degree. So what is the critical angle for glass water interface? This should be equal to mu G sine C is equal to mu W sine 90 degree. So critical angle for this will be mu W by mu G. Like this, for a pair of medium, we can define a critical angle of a system. Now, similarly, if a ray of light, let this be the boundary. Let this be the interface. So it can happen that for a grazing incidence, there's a denser medium, there's a rarer medium. For look at the what is angle? This is the angle of incidence. So then this will be critical angle. This is incident ray. This will be now refracted ray. Then what is the condition now? Mu1, mu2. So we can write here, or mu r, you write it. Mu r sine 90 degree is equal to mu d sine of critical angle. The same thing. So for grazing incidence means this is a boundary, no? This is the boundary. This everything is a boundary. If a incident ray grazes boundary, then the refracted ray will emerge at an angle, critical angle with respect to normal. This will be the normal. We'll call this as normal. Sir, how come if it is grazing, then what makes it to like a deviate here? It can proceed further straight like this. This is a typical question what many will ask here. Means if a ray is incident, grazing incidents, then we should continue to move. No? We should proceed further. What makes it to deviate like this? In fact, here it is not like angle of incidence 90 degree. The angle of incidence will be slightly less than 90 degree. The angle of incidence will be around 89.99 degree, but not 90 degree. Then definitely 89.99 approximately we can put it as 90 degree. There's a main idea of this one. So this idea will be using exclusively in the prisms. You have to grazing incidence, grazing emergence. So what is the basic condition for a for a ray to undergo TIR? The angle of incidence must be greater than or equal to critical angle. There's one basic necessity condition. And when do this TIR will take place? Only when the ray moves from denser to rarer. Okay, fine. So in coming class, we'll discuss the next concept. Thank you all of you.